What did we do last time? What we did? Whatever's bad. And what else? Spanning set, yeah. And what else? Right, spanning set, linear dependent. So kind of started discussing the notion of a minimal spanning set. So recall, we say that a set spans a vector space if every vector in a vector space can be written as a linear combination of the vectors in the set. And linear independence just means that none of the vectors in your set is a linear combination of the others. Right? And then the idea of the minimal spanning set was a set that spans your vector space with as few vectors as possible. So a spanning set that's linearly independent. This is what we call the basis. And so the vectors v1, v2, vn form a basis for a vector space V if and only if they're linearly independent and they span V. So relations between spanning sets and linear dependence, we're going to look at some relations, or a relation. If v1, v2, vn is a spanning set for a vector space V, then any n vectors where n is greater than or equal to n is linearly dependent. Right? So if you already know you have a spanning set, so it takes, you have n vectors that span a vector space V. If you add more vectors to that spanning set, it's automatically linearly dependent. Right? Which makes sense, right? Because you're taking a vector from your vector space, which is already a linear combination of those vectors, putting it in the set. It has to be dependent. Keep in mind, it's not saying that that set's already linearly independent, right? We don't know if it's independent or dependent. It doesn't matter. As a corollary, if both of these sets, v1, v2, vn, and u1, u2, un, are bases for a vector space V, then n equals n. Right? Any basis for a given vector space has to contain the same number of vectors. Well, that's interesting. So the number of vectors it takes to form a basis is always the same for a vector space, so why don't we define that? We call that the dimension of the vector space. And so the dimension of a vector space is just the number of vectors contained in a basis. And as the previous corollary just stated, every basis has the same number of vectors. So just as a guess, we already know that vector spaces have to be non-empty, right? They have to contain one vector. And that one vector, by the properties, or by the axioms of vector space, has to be the zero vector. So if you consider the vector space of only the zero vector, what do you think its dimension is? 0. Its basis would have to be empty. Sadly, there's no rule that says that a vector space, the basis for a vector space, has to have a finite number of vectors. If it does happen to have a finite number of vectors, we just say it's finite dimensional. Otherwise, it is infinite dimensional. So it is possible that you get a vector space that isn't spanned by a finite number of vectors. You need an infinite number of vectors to span it. That is infinite dimensional. Now for the good news. 99% of the vector spaces we work with in this course will be finite dimensional. I say 99% because I'm actually not confident that there's no infinite dimensional vector spaces. I don't know if I mentioned any.
What's an example of an infinite dimensional vector space?
I couldn't even come up with one on top of my head.
So
But I wasn't really algebra focused either in my studies, so I'm sure they're out there, right? But I haven't really delved into the algebra because most of the common vector spaces are all finite dimensional. The matrices, polynomials. Oh, maybe infinite degree polynomial. Right, just set up just a vector space of all polynomials. That would probably be infinite dimension, right? Because I'm not limiting the degree, so you have to keep adding. So that would probably be your easiest example of an infinite dimensional vector space. A relationship between dimensions, span, and linear independence. So let's just say we have a vector space of dimension larger than 0. Any set of n linearly independent vectors spans V. Any n vectors that span V are linearly independent. No set of fewer than n vectors can span V. Right, so that one's fairly obvious. And the easiest thing to think of is think of 3 space, right? Ordered triples. You can't have 2 vectors span 3 dimensions, right? You have to have 3. Right? That'd be like saying that I can describe all ordered triples with just x and y. Now there has to be a third point. Any subset of fewer than n linearly independent vectors can be extended to form a basis. That's pretty important. As is the next one. Any spanning set that contains more than n vectors can be pared down to form a basis. Right. So again, going back to just R3. You have two linearly independent vectors, you can add another vector to span. That would guarantee that it spans R3. That's what property 4 says. Right. And property 5 is saying, let's say you have 5 vectors in R3. You can eliminate 2 of them to form a basis. Notice, though, what they don't tell you, 4 and 5. 4 is not telling you which vector to add. Right? It doesn't tell you how to determine those vectors. It just says, it just guarantees that you can add vectors. And same thing with 5. It's not telling you how to choose which vectors to remove. It's simply guaranteeing that you can remove vectors. I like started with these. And then it sounded like calls at the end.
Keep on saying.
Those are the worst though. It starts off the sneeze and you wind up coughing because you choke on the sneeze. That's awful.
I think if you're getting the recurring basis, you kind of go into cough, and then you get that weird tickling feeling back in the back of your throat.
That's why I never hold coughs back.
Yeah, but so.
Well, that's actually not true. Sometimes I do, but that's only so I can get closer to my kids to cough in the face like they do. Turn around, spare flight. Cough in my face, get me sick, I'm going to turn the paper. If you want my grade, they got me sick and not my wife, and I'll cough in my wife's face together, so share the love. Does this set form a basis of R4? If not, we're going to determine the dimension of the subspace of the span of S. Right, so what does it mean to form a basis? What has to be true? And span R4. Dimension of R4. So honestly, all we have to do is check to see if they're linearly independent. Because there's 4 vectors in there, right? So by, what is it, property 1, if those 4 vectors are linearly independent, they automatically span. So let's check for linear independence. How do we check for linear independence from last time? finding a linear combination?
Checking if it
Well, it's guaranteed to exist. Okay, so I can just make all the constants zero. There's a zero factor. So making sure it's the only solution is the trivial solution. Right, so that's the definition, but how do we do it? And just so we don't write out all the work all the time. Remember how we checked for linear independence? What did we do last time? Of what?
The matrix where each column is one vector.
Set up the matrix where each column's a vector in the set, right? And then row reduce it. If it's linearly independent, what's that going to row reduce to?
Identity.
The identity. So first column, first vector. Second column is going to be the second vector. Third column will be the third. And then finally 2, 6, 3, 5. And we want to row reduce that. You do not need to worry about doing it by hand. Right, I already tested you on that. At this stage of the game, remember what I said when we first introduced this? I said 95% of linear algebra is now row reducing. And this is why. So I'm now just wondering, can you interpret the row reducing one? I think I did the calculator last time, so I'm just going to use Mathematica this time. Look at that one. Use Mathematica in the course. Remember, that's how you set up a matrix in Mathematica. Braces around the entire thing, and then each row is its own set of braces. And to actually make sure the output's in matrix form, I wonder if right. Oh, I could do that too. Let me see how that works. Matrix form command. Let's see if that works. It does! Yay! I think that must be a new command, so I have to remember that. There's our row reduced echelon form. A word of caution now. If this was an exam question, and you use your calculator to row reduce it, it's going to be pretty difficult to get partial credit if you typed it into your calculator wrong, isn't it? Because then I'm not sure if you typed it in wrong and you don't know how to do row reduction. So just make sure you're very careful when you type it in. So what's your conclusion? Independent or dependent?
Dependent.
And I think I called it set S, right? Yeah. Is this a basis? Okay, that helps me out there. How did it? Let me see it. The way things have been going lately, let's hope we don't hear a big boom. That would not be good. I would not excuse class. We're still having tax day, isn't it?
But no taxes for 30 days.
There's a nuclear explosion the day of the exam, that's not an excuse not to take the exam. I'll still be here. Extra arms and all. I make use of those extra arms too.
When you die of that organ failure, is there a capacity?
Depends on how much radiation.
There she is.
Again, depends on how close you are. Obviously, ground zero, yeah, you're dead. Although I don't think it's the radiation that kills you at ground zero. It's probably the intense heat that literally melts you.
And that would be the shock wave that would probably rupture all the organs.
Well, again, ground zero, the shock wave's not going to kill you. You're going to be dead long before that. You're going to be dead from the intense heat.
You're gonna come back from the grave just to make.
Oh, yeah. Oh, absolutely. Zombie apocalypse and joining the zombies. Are you kidding me? I joined the winning side.
Just imagine your wife going up to the before just to monitor us.
No, I'm not. I'm also not very loyal. Highest bidder. Combine my loyalty. Second part was, since it's not a basis, oh, come on, use your inner eye. Second part was to determine the dimension of the subspace that is spanned by these vectors, right? Oh, I think I said wrong, but go away. All right, so we know that this spans some subspace, right? And we know that because we mentioned last time, remember, that the span of a set is a subspace. Well, if we go back to property 5, spanning set that has more than n vectors can be pared down to form a basis. Right? Clearly, we have more than n vectors in the subspace for the span. So we can just remove vectors from it to form a basis. which vectors do we remove? If we look at the row-reduced form, do you interpret that? Which vector or vectors do you think is a linear combination of the remaining? How do you determine that?
Because it's the only one that is in, well, where there are three pairs.
You were getting there. Doesn't have a leading one, which in a sense means, yeah, it's gonna have three variables. It's a free variable. Right, so column 4 has no leading ones. So we could write 2, 6, 8, 5 as a linear combination of the remaining 3. So remove it. What you're left with will now be linearly independent. Typically, I'll represent basis with a script B. It's just any set, it doesn't matter, but basis B, we're not very creative. That would then form a basis for the span of S, right? If you don't believe me, you can check to make sure that they are indeed linearly independent. We already know they span, because that's the definition of span of S, right? So what's our dimension? Say it loud and proud. 3. That wasn't very loud though. So look at that. Even a question that involves calculation still requires a lot of logical reasoning. Welcome to your new world of mathematics. Just you wait till you take your first level 300 physics course. Find a basis of R4 that contains those two vectors. Now, What is the dimension of R4? 4, right? That means we need to add 2 vectors, right? The basis has to have a total of 4 vectors. Oh, but wait a minute. All right, so here. Here, this one right here. We know that we're going to need 4 vectors in the basis, which means a set of 4 vectors would form a spanning set. Any vectors above that would also span, right? Because I don't know what 2 vectors to add. But I do know the standard basis for R4. I'm going to add those 4 vectors into our set. And then from there, determine which 2 to remove. Oops. And I'm going to write it in such a way that it guarantees to remove vectors other than these 2. I'm going to write the 2 vectors I want in my basis first. And now I'm going to add the vectors from the standard basis of R4. So here's the set that I'm looking for. Or here's the set that I'm considering. We already know that's going to span R4 because it contains the standard basis. And the standard basis spans R4 by definition. Which would now allow us to use property 5. We can pare this down to a linearly independent set. Oh, but that is the exact same process as we did here. So set up your matrix. So go ahead and type it into your calculator. while I type it into Mathematica. It's important that you learn to do this in your calculator now because I will not help you on the exam to figure it out. Which vectors are we going to remove? Which are what ones?
0, 0, 1, 0, 0, 0, 1.
I did something different for the matrix.
Make sure that you typed it in right.
They'll figure it out later.
I just got a box in the two in the last.
Yeah. And
That's
then,
all it was.
Oh, did I look at it wrong? It's possible I looked at it wrong.
yeah, I
Well.
just do things.
Forward. Because in my notes, I also have a 1 there. But on Mathematica, it's a 2. Oh. I see it. Okay, I typed it in wrong. And that should be a 1. That would be our basis. That contains the 2 vectors of interest. Is that the only correct answer? Not right. Problem is finding the other two vectors you want to add. This is probably the easiest way to go about it. Just add in your standard basis and then we'll figure out which ones to remove from there. Good so far? Now look at that. 2 problems, 2 row reductions. All right, so on an exam, if you set up a matrix and row reduce it, you're on the right track. All right, because chances are the problem's going to require you to row reduce a matrix anyway. Find the dimension of the subspace W of R3. And if you remember correctly from last Thursday, we proved already this was a subspace of R3. So since W is a subspace of R3, what can we say about its dimension? Can it be larger than the dimension of R3? Could it be smaller? And it could also be the dimension of R3, right? So we already know that it's going to be less than or equal to the dimension of R3. What's the dimension of R3? Dimension of R3 is going to be 3. So let's just create a set of 3 vectors that are in W and check to see if it forms a basis. I'm going to form a standard basis. Probably the easiest 3 vectors to see that are in W. And I'm also going to specify that clearly this set is contained in W. Right, because that's important. You can't have vectors outside of W to form a basis of W. So clearly that set of vectors is contained in W. We claim that this set does indeed span W. Are we allowed to just make a claim? No, what else do we have to do? We have to back up the claim. This. Not going to erase this. So I let A, B, C be a vector W. Want to row reduce this, however, do not use your calculator. I'm going to tell you you're going to get 0, 0, 0, 1 at the bottom if you use a calculator. So we're going to do this by hand anyway. But this is fairly simple to do, right? Row 1 plus row 2. And then row 2 plus row 3. Would give us this, right? But what do we know about A plus B plus C? 0. We've just proven that there exists constant C1, C2, C3, such that ABC is a linear combination of the vectors in S. Implies that S span is W. And so the proof is complete for that. That's row reduced, right? Then this would be the row reduced matrix. Right? If we just look at the zero vector, A equals B equals C equals 0. Would these vectors in S be linearly independent? So which vector can we remove? Right? In other words, which vector is a linear combination of the others? The third vector, right? Eliminate the third vector to get your basis. So by eliminating that vector from S, we form a basis for W. That means that set there forms a basis for W. So what's the dimension of W? So our dimension is 2. Good. This is probably the only thing that really sucks about this section. It just takes up so much space. Let W be the subspace of R4 spanned by those 3 vectors. We want to find a basis for W and determine its dimension. What is the largest number of vectors a basis for W can contain? 3. Right, because W is the set spanned by those 3 vectors. And so either they're already linearly independent, in which case we have our basis, or they're not. In which case we have to eliminate one or more vectors to form our basis. We're already told that that set spans W, right? So all we have to do is check for linear independence. And how do we check for linear independence? Which matrix? Each column is what? Is a vector, right? So let's make the first column 1, -2, 5, -3. And this is exactly why, by the way, I started to do my matrices by column instead of row. Because of this stuff right here. Reproduce that. Go ahead.
By column 1, 0, 0, 0, 0, 1, 0, 0, -1, 2, 0, 0.
Does that prove linear independence? No, so these are linearly dependent, right? So how do we form our basis? How do we form a basis for W? What about the third column? So be careful, not column. Right, remove the third vector from the set. And what is the dimension for W? And there you go. So extend the basis that we just found to form a basis of R4. So actually what I might do is skip on to question 6 for now and then come back. Because then there's question 5, which is much like what we've been doing. I do want to examine this one. So W, subspace of M22. M22 is the vector space of 2 by 2 matrices. We're saying W is the subspace of 2 by 2 symmetric matrices. We're going to show that W has dimension 3. What does it mean for a matrix to be symmetric? Now, when you're dealing with a square matrix, or in this case, a 2 by 2 matrix, that would mean that whatever you have, let's call it the off diagonal. The off diagonal has to be the same. And so main diagonal, you'd go left to right, the off diagonal would be right to left. That would be in W, right? That's a 2 by 2 symmetric. That's 2 by 2 symmetric. That's 2 by 2 symmetric. Start with that. Clearly, that's contained in W. Consider this system. We're going to show that this system is consistent. Right, so what I'm trying to do here is check to see if this set spans W. So let's write out what W looks like. And that's what all 2 by 2 symmetric matrices would look like. Well, look what we get. C1 equals A, right? And C2 equals B, right? C2 equals B, and look, C2 equals B. We get it twice. And C3 equals C. System's consistent, so S spans W. Is the set linearly independent? Well, set A, B, and C ought to be 0, right? That will give you the 0 vector in our vector space. That gives C1, C2, C3 all 0, right? That's the trivial solution. Which means the set is what? Independent or dependent? Oh. So that set, S, that I just formed, spans W and is linearly independent. Doesn't that mean S is a basis? Well, how many vectors were in that set? 3. So what's the dimension of W? Ah, that's what I wanted to prove. All right, so now this is where the vocabulary can kind of get confusing. Right? Because notice I called each of these a vector because they're elements of a vector space. Right? So I don't mean vector in the normal sense of vector, because clearly they're not like vectors. But they are vectors because they're in a vector space. Welcome to the beautiful world of mathematics. Questions on basis and dimension. My lab homework on this, again, will be due on the 27th. That's 2 weeks from today. There will be an assignment for spring break. Pretty nice assignments, nothing too difficult. If I remember the prompt correctly, you need to pick 3 problems from the course, plug them into AI, and you got it, and analyze the solution. Right. So you're going to copy the prompt, copy the response, and then give an analysis on the solution. What did it do right? What did it do wrong? Point out the mistakes. Easy stuff like that. So again, really easy assignment. And also to kind of get you used to AI, get you looking at AI and where it's useful, where it's hard. So that will be over spring break. That will post on the 18th at midnight and be due the 24th before the end of the day. And there is an extra credit opportunity on that as well. So just read the prompt once it goes up. Have a wonderful and safe spring break.